Yes. Atomic vibrations, the scattering of electron due to the atomic vibrations, that depends on the temperature. While all other scattering types like impurity scattering and residual resistivity, that depends only on the concentration of impurities as well as defects. Then we also saw that these uh, these resistivities can be simply added together because of the Mathiessen's rule. Right? Mathiessen's rule basically tells us that all the scatterings, the resistivity due to all the scatterings, that can be added together. And then finally, in the last class, we discussed how impurities, how we can predict the resistivity which is caused because of the impurity scattering. And that was given by Nordheim's rule, right? We saw this. We saw the Nordheim's rule, which simply says that the resistivity due to the impurities will be Cx times 1 minus x, where x is the solute concentration and C is the Nordheim's coefficient. Then we discussed some examples like if we have quenching and annealing, there can be ordered solid solution because of that. The resistivity, there can be sudden falls in resistivity. Then there were some empirical relations which we saw for the mixtures, like the series rule of mixture, parallel rule of mixture. They are actually simple to derive. Also, I mean, you can draw the analogy from electrical circuits also. And there were some. These are the empirical relations actually where there is a random distribution or uniform distribution of solute in the solution. Then we can have different types of relation based on the resistivity of the dispersed phase and the continuous phase. And we saw this picture, right? In the towards the end, we saw that when we are in the when yes when we are in the single phase region, basically the solid solution region, then the resistivity will be given by the Nordheim's rule. And when we are in the two phase region, alpha plus beta region, then the resistivity will be given by mixture rule, right? So these things we already saw in the last class. Any questions so far? Whatever we have covered, if you have any questions from the previous class, we can address them now. Otherwise, we can start with the new topics for today. Okay. So then, if there are no questions, let us. So far, we have only dealt with the resistivity of or the uh, electrical conductivity of metals. Now, let us look at what happens when we don't have metals. Like non-metals can be ceramics as well as polymers, right? In the non-metals, we can have ceramics, or we can also have ceramics, glasses, as well as some of the polymers. Like this PET is a polymer, polypropylene is also a polymer. So one thing is very clear from this plot, that electrical conductivity for all the non-metals is much lower in comparison to the metals, right? If you see here, metals, the electrical conductivity of metals lies somewhere in the range of 10 to the power 4 to 10 to the power 9, right? And most of the ceramics as well as polymers, they have much lower electrical conductivity. Silicon is also actually a semiconductor, but when we dope it, like when we dope it with boron, or let us say nitrogen, or phosphorus, then we can have higher electrical. We can increase, we can manipulate the electrical conductivity of silicon. We will see how that can happen. But intrinsic semiconductors, which means pure semiconductors, sorry, pure ceramics as well as semiconductors, they have very low electrical conductivity. Only when we dope them with certain elements, then we can have higher electrical conductivity in semiconductors. Semiconductor is a special class of material. We will discuss how that can happen. Okay. Now let us see what happens in ceramics. To discuss this slide, actually, first let us just recap what happens in metals. In metals, there is metallic bond, right? Metallic bond means there are a lot of electrons which are shared by all the atoms which are present in the crystal. there is no localization of the electrons, right? It is, you cannot say that this electron, this particular electron belongs to a particular atom. That does not happen in the metallic bonding, because actually in metallic bonding you have sort of free electron gas or electron cloud, which is shared by all the atoms. So electrons are very free to move around in the crystal, or in another language you can say that they are not localized. They are not localized to a particular atom or a particular bond. They are shared by all the atoms in the crystal. Now, in ceramics, we know that in ceramics actually we have very strong covalent bonds. Covalent bond is one of the strongest bond, right? It is stronger than metallic bond as well as other bond types which we have seen in the first chapter. So covalent bond are very strong and it is very difficult to break them. Okay. So because these bonds are very strong, there are no free electrons. Basically, the electrons are localized. They are localized to that particular bond and shared between only between those two atoms which are forming the bond. In this case, let us say here, if you look at here, there are two covalent bonds, right? And these two covalent bonds will have two electrons, right? And these two electrons will be shared, sorry, they will be having four electrons, and these four electrons will be shared only between these two atoms. They will not be shared by any other atom which are in the neighborhood also. Okay. Because of this, the electrons are actually not free to move around in the crystal. So then how do we have electrical conductivity? Because we know that to have electrical conductivity we need some charge carriers. In metals, free electrons are charge carriers. In this case, in ceramics also we get some free electrons. How that happens is actually there are, we know that at any finite temperature there will be thermal vibrations of the atom, right? Atoms will be, let us say if we look at this particular atom, it will be vibrating around its equilibrium position in all the directions actually. Not only in this direction but actually in all the directions it will be vibrating. And because of this vibration there will be elongation as well as contraction of this bond. If we are looking at this bond, let us say, then there will be elongation as well as contraction of this bond, right? And when we have, I don't know what is happening with the pen, but anyways, I think it is understandable here that when we have enough elongation, then there will be bond breaking, or we can also say that bond will be ruptured. And when the bond breaks, there will be a free electron which will be generated. Here we can see that there is a free electron which is getting generated, which is getting free from this bond. And then once it is free, then it is actually go and move around in the whole crystal. Let me just clear this slide a little bit. There is a lot of yes. So when this bond is broken, this electron gets free, and because there will be a lack of electron or lack of charge, due to that there will be a positively charged hole which will also be created. So when one bond breaks, there will be generation of an electron as well as a hole, right? And then once we have this hole, what can happen is electron is anyway now the electron can now anyway contribute in the electrical conductivity, but hole also contributes. How hole contributes in the electrical conductivity? Actually you can see here we have hole here, right? So electron from a neighboring bond, it can jump from, it can jump, so it can jump from this bond to this bond. The electron will jump here, that means effectively actually, and then actually this bond will be reformed again, and there will be a broken bond in these, between these two atoms. So effectively the hole has moved from this position, from this position to this position. So we will have electrical conductivity due to both the electrons as well as holes. Electrons will normally, like it happens in metals also, they will be moving around in the crystal and they can contribute in the effect of an electric field. They will move in the opposite direction of the electric field. And holes which are positively charged, they can also move around in the crystal by exchange in the with the neighboring bonds, right? So but holes will be moving in the opposite direction because they are positively charged, right? When we apply electric field, they will be moving in the direction of the electric field. So electrons and holes both will contribute, but they will be both moving in the opposite directions. Okay. And one more. This is one way of generating the free electrons in a ceramic. We can by the bond rupture. By bond rupture, we generate these free electrons. But there can be other ways also, which I mentioned earlier. Also by intentional doping, also we can generate free electrons. Intentional doping means, let us say, if we have silicon has four valency, right? So if we have, let us say, phosphorus, which has five valence electrons, if we substitute in one silicon atom with phosphorus, there will be one extra electron, right? And that electron will also contribute in the electrical conductivity. And that is why actually these semiconductors, where you can generate these kind of free electrons by intentional doping, they are very important. You must be knowing that all the semiconductor devices, all the devices which we see today, right? Most of the devices like mobiles, um, desktops, laptops, wherever we have these electronic devices, 90% of the time we are looking at the material which is called silicon, but that is not pure silicon. We have to always dope, because pure silicon has a very low electrical conductivity. We can see here, right? Intrinsic silicon has a electrical conductivity of only 10 to the power minus 3. But when we dope silicon with appropriate impurities or appropriate dopants, then we can increase the electrical conductivity of silicon up to 10 to the power 3 also. So that is why these semiconductors, they become very interesting class of materials. All right. So because both electrons and holes, they are contributing to the electrical conductivity. The electrical conductivity of a ceramic, it comes from both electron as well as hole. Here we have E is the charge of electron, N is the concentration of free electrons, and mu is the drift mobility of electrons. And similarly, we have one term for holes also. We have the charge on a hole, then concentration of the holes, and drift mobility also of the holes. So we can have electrical conductivity due to both electrons as well as holes in the ceramic. Another class of material is also, we are not going into too much detail, because we will be having a separate chapter on semiconductor, so we will discuss these things in much more detail actually in the chapter afterwards. But here I just wanted to give you a flavor how basically electrical conductivity can happen in ceramics, where there are very low number of free electrons. There is a query, let me just have a look at it. I am having confused. I will just paste the query here also, so that you can also see the question. So the question is, I'm having a confusion as to, in the structure you are showing all atoms are same, only right. All atoms are same, only right. So you are saying that one electron that meaning bonds gets free to move and other remains in the atom. Is it possible that it can happen as two atoms are identical? Yes, I mean, see, it is coming, the free electron is coming because of the rupture of the bond. It is not coming directly, it is not coming like, this electron is not one of the electrons which is localized at the atom itself. This electron is localized between these two atoms because of the bond formation. When I think you remember from the first chapter, when we form the bonds, the electron density is centered in between the atoms, right? And because of this, when the bond breaks, then this electron which was shared by the two atoms, that gets free. We are not getting, we cannot tell actually this electron whether it is coming from this atom or this atom. It could have come from either of these atoms, because it has lost its identity. Now it is shared between these two atoms only. All right. So the atoms, because the electron is not coming from the atom, it is not necessary that all the atoms will behave similarly. First of all, also one more thing is also that the atomic vibrations, the frequency of atomic vibrations is not same across the crystal. Some of the atoms, you will see actually there is a distribution of these atomic vibrations. Some of the atoms will be vibrating with more frequency and more amplitude, and some of the other atoms will be having less energy and because of that, the other bonds will not be broken. Only certain bonds where there will be enough energy, only those bonds will be broken, and because of the breaking of those bonds we will have free electrons. Is this clear now? Is your did I answer your question? Okay, yeah, all right. So yes, this is in a very broad way the mechanism of electrical conduction in ceramics. Let us look at the ionic crystals and glasses. Ionic crystals means, like for example, NaCl. In NaCl we will have one positively charged atom and one negatively charged. For example, sodium will be positively charged and chlorine will be negatively charged. These there In these kind of materials also, thermal equilibrium actually requires that there will be certain concentration of vacancies at and interstitials. So for example, here there will be some atoms which will be missing from their positions, and there might be some atoms also in the interstitials. This is an interstitial and this is a vacancy, right? Once you have these kind of vacancies and interstitials, they actually play a role in electrical conductions in these kind of ionic solids. So what can happen is that once you have certain concentration of vacancy, the ions can move, right? For example, this ion which is here, positively charged ion, it can move from this position to this position, and effectively the vacancy will move in the opposite direction, right? So because of this vacancies, similarly it will happen for the interstitials also. It can move from one interstitial side to another interstitial side, and that's how both the vacancies as well as the interstitials, they can contribute. In ceramics as well as metals, it was not possible because the atoms itself, they were not ionized, they did not carry any charge, right? And it was very difficult to move also because the bonding was much more stronger. In this case, because the atoms which are there in the crystal, they are charged, they can play a role in electrical conductivity, right? Vacancies can move as well as the interstitials can also move from one side to another side. And in the effect of the electric field, of course, they will move in the direction of the electric field based on their charge, right? So that's how these vacancies and interstitials will also play a role in the electrical conductivity. This is an ionic solid. Similarly, for glasses, usually glasses also have a certain concentration of impurities. For example, this is what we are seeing in this picture is a silica glass. Silica glass is used very commonly. Okay, there is a question. I will just come to that. Give me a moment, and then I will address your question. So let me just discuss this part here. So in this is what we are seeing here. It is a silica glass, right? They have certain type of bonding in the material, but there is a certain concentration of impurities. Sometimes it is intentional doping also, we can say. In glasses we have certain concentration of impurities because of the thermal equilibrium, but we can also introduce these kind of impurities also. And then for example, here in this case, the atoms which are in the matrix, they are not charged, but these impurities are charged, like sodium impurity in the silica glass, that is having a positive charge. So it can jump from one ring to another ring, and that will basically play a role in the electrical conduction of these material of these kind of glasses. Okay. There is a uh, there is a question, sir. Ceramics are insulators or semiconductors? So ceramics can be both insulators and semiconductors. We can say that all the most of the semiconductors which we see today, they are ceramics, but all the ceramics are not semiconductors. Okay, it depends on their band uh, band structure, which we will just actually we will start probably in the next class. It depends on their band structure and band gap. Okay, based on that, certain ceramics, for example silicon is a ceramic, but other ceramics like alumina is a ceramic, but it is not a semiconductor. Silicon is a semi ceramic as well as a semiconductor because of its band structure, and band structure is a very fundamental property of a material. Okay, so it comes from there actually, whether a ceramic will be a semiconductor or not. Okay, I hope that clarifies. Some ceramics, for example, alumina is a very strong insulator, but some of the ceramics like silicon or zinc oxide, they are ceramics as well. At the same time, they are also semiconductors. So in this case, we can see that actually the electrical conductivity, the conduction of charge, that is happening actually through the diffusion of atoms, right? For example, in this first case, in the case of ionic solids, the charged ion has to move from one vacancy side to another vacancy side. Basically, one atom is diffusing from one side to another side. It is an atomic diffusion. Similarly, here also, sodium ion is diffusing from one side to another side. So conduction is essentially drift by diffusion, and it is directed by field. Directed by field means it will be the direction will be defined. Direction will be decided by the direction of the electric field. But the drift is happening because of the ionic diffusion. So first of all, the electrical conductivity of these kind of ionic solids, where there can be I mean in this case we saw only one impurity, or so only two types of ions, but there can be different types of impurities, like sodium can be also there, potassium can also be there, chlorine can also be there. So electrical conductivity will be addition of electrical conductivities of all of them. So basically, all of them will be contributing in the electrical conductivity of ionic solids as well as glasses, where we can have multiple type of impurities. Okay, Qi here is the charge carried by the. Actually, it's just another form of any mu, right? We saw sigma is equal to n times E times mu. Where here we have Qi, which is the charge, Ni is the concentration of the impurity, and mu I is the drift mobility of that particular impurity. All right. In the earlier case, we saw that temperature dependence in case of metal, right? It was rho is equal to rho is equal to AT, or sigma is equal to 1 by T, right? The electrical conductivity of metals was inversely proportional to the temperature. In this case, we get a exponential dependence. Why that happens is because this point which I just mentioned. In this case, conduction is essentially drift by diffusion of atoms. And diffusion of atoms, you might be remembering from your previous classes also, like previous courses during JEE also, that atomic diffusion is a it follows RNA's type of relationship, right? RNA's temperature dependence of conductivity, which we can see here. There is a sigma is equal to sigma naught exponential minus E by KT. E sigma will be some activation energy, right? Activation energy for moving of ion from one position to another position. K is the Boltzmann constant and T is the temperature. It is due to the diffusing nature of the charge conduction. Charge transport happens through the diffusion of charge carrying ionic species. Diffusion is the key word here actually. Because of this diffusive nature, we get this certain temperature dependence, RNS type of temperature dependence. This has been validated experimentally also. You can see this is a plot of, it is a log and inverse temperature plot. Conductivity is on a log scale and temperature is on the inverse scale. And we can see according to this reaction, it should be a straight line, right? And here we can see that for most of the ceramics, silica is a ceramic, PVC is a polymer, and this is a glass, sodium glass, right? For all these, this relationship is followed very well, because the conduction is happening because of the ionic diffusion. All right. Sir, in glass only impurities will diffuse. Yes, that is correct. Because see, in glass, we don't have the charge on other atoms which are forming the bond. They don't have any charge, because these are not ionic bonds. These are actually strong covalent bonds. In glass, we have these strong covalent bonds. So they will not be contributing much to the electrical conductivity. Only when there is a bond breaking or some bond rupture, then there can be a free electron. But that is very difficult. We already have free ionic species which can contribute to the conduction. So their contribution will be dominant in the electrical conductivity of a ionic glass. Okay. In the same slide in left diagram, is it okay? What material, like it? Is it ceramic? No, it. This is a ionic solid. ionic solid is, it's not necessary that ionic solids will always be ceramic. For example, sodium chloride, right? Sodium chloride is an ionic solid, but it is not a ceramic. Ionic solid is also a different category of materials. All right, it's not necessary that they will be ionic. These are actually ionic bonds. Ionic solids are defined by ionic bonds which they have. In ceramics, you can have, as we saw, mostly you will have covalent bonds. And ionic solids is a different category of materials. They can have, so I mean, I gave you an example of sodium chloride. It is a solid, but it is not a ceramic. It is an ionic solid, but it's not a ceramic. Okay. Yes. So in this, these are actually experimentally measured electrical conductivities, and we can see that they follow the Arrhenius relationship very well. Okay. Any questions so far on the electrical conductivity of? We have dealt this topic in very briefly actually, because we are more concerned about the metals. In this course actually we will be talking more about metals and semiconductors, and there will be a dedicated chapter, like there will be some good amount of discussion on electrical conductivity as well as thermal conductivity of semiconductors. So we have left it for the later discussion. Right now we have just, I have just tried to give you a flavor of the mechanism through which electrical conduction happens in non-metals. Any questions? Okay. If there are no questions, we will also look at thermal conduction today. That will also be a brief discussion actually, because thermal conduction is not really a focus of our, I mean, in this course. This is because the course syllabus wants us to discuss a little bit of thermal conductivity also. So that's why we will dedicate some of our time for discussion on thermal conduction. So first, let us discuss the how the thermal conduction happens in metals. Right? In metals, we know that there are a lot of free electrons. Right? Electrons are charge carriers, and when we look at thermal conductivity, electrons are also the heat carriers. How they become heat carriers? Actually, what happens is electrons are moving around in the crystal. Right? In metal, there is an electron cloud, and electrons are moving freely into the crystal. And we also saw earlier that atoms are vibrating, isn't it? Atoms are vibrating around their equilibrium positions, and amplitude as well as energy of their vibrations, that depend on the temperature according to the kinetic molecular theory. We discussed that earlier also. Although electrons don't follow the kinetic molecular theory, we can still consider atoms to be following the kinetic theory. And according to kinetic theory, the energy of each atom or vibrational energy should be equal to of the order of kT by 2, right? So as we increase the temperature, their energy will also increase. The energy of their vibrations, that will also increase. And because, so what happens, let us say if we are heating this side of the metal and this side of the metal is cold, so what will happen, the atomic vibrations on this side of the metal, they will be much stronger. They will be carrying much more energy, I mean more energy in comparison to the side where the temperature is low. You can see the size of these arrows also. The size of these arrows actually is showing the amplitude of the vibration. So on the hotter side, the amplitude of vibration is much larger in comparison to the amplitude on the colder side, right? So basically they are carrying more energy. There is more vibrational energy on the hotter side, and when these electrons are traveling, they collide with these atomic vibrations. Once they collide with the atomic vibrations, they get basically some of the energy of these vibrations that gets transferred to the electrons. So electrons start moving, because of basically electrons gain some energy, and because of that their velocity will also increase, right? Because they gain certain energy, their velocity, their kinetic energy will be increasing, and because of that their velocity will also increase. And when these higher energy electrons, they travel to the colder side, what happens is that they will collide with these atoms which are vibrating slowly, and they will transfer some of their energy to the these atoms, right? And that will increase their energy, and they will start vibrating with more frequency. So that is how the energy will transfer from hotter side to the colder side through the medium of electrons. Electrons become the heat carriers in this case. Okay, so that is the mechanism of heat conduction in metals. There is a question that electrons should have same amplitude as you told previously that they are independent of temperature. So why there is different size of arrows on electrons? We have actually the question somebody is asking is electrons, the energy of electrons or the velocity of electron is temperature independent, right? So then their velocity should not be dependent on the temperature, but we are showing larger arrows for the velocity of the electron on the hotter side. The reason for that is basically this, the gain in energy is not because of the electrons. Gain in energy of electrons, sorry, I think I did not say it correctly. Gain in the energy of electrons is not because of the temperature. It is coming because these electrons are colliding with these atoms which are vibrating with more energy, and their energy is getting transferred to these electrons, and because of that they gain higher velocity. That's a very good question actually. That the gain in energy of the electrons is not because of the temperature actually. It is coming because of their collision with these atoms which are vibrating with more energy, and their energy is getting transferred to the electrons. And when they travel to the colder side, they transfer their gained energy to the atoms which are vibrating with less frequency. Okay. Does that answer your question? Yes. Okay. So in this case, we can see that actually electrons are carrying both the charge as well as heat. So they are carriers for thermal conductivity as well as electrical conductivity. And naturally, that there is a slide missing. It looks like. Okay, we will. This is, I think you already know that, right? The definition of heat flux, dq by dt, which is the rate of heat transfer. That is like here basically in this picture what we are showing is that the heat is getting transferred from hotter side to the colder side. This is a cylinder, and dq by dt, which is perpendicular to this cross section, that depends on del t by del x as well as cross sectional area, right? This I think you must have already seen. And that is how we get the Fourier's law, which says that dq by dt should be proportional to area of the cross section as well as temperature gradient, and then constant, the proportionality constant k, that is actually the thermal conductivity, right? I think this is yeah, very old news, and you all must be knowing about this. This is the Fourier's law. And when we draw parallel, we can draw a parallel with the electrical conductivity also with the Ohm's law, right? Ohm's law is, here we were talking about, this is actually a sort of heat current, isn't it? Here we are talking about electrical current, and that is also proportional to the area, cross sectional area, and voltage gradient. And proportionality constant is known as electrical conductivity. So because of this parallel nature as well as electrons participating in both the electrical conductivity as well as thermal conductivity, for metals we have a definite relationship between electrical conductivity and thermal conductivity. The ratio of thermal conductivity and sigma T, that is a constant. This constant is known as Lorentz number. This constant is known as Lorentz number, and the value of Lorentz number is, this is the expression for that, and when you calculate, this will come out to be 2.45 into 10 to the power minus. This relationship is only for the metals. We should remember that, and that is happening because actually electrons are participating in both electrical conduction as well as thermal conduction. All right, and now we know that, right? That sigma is equal to AT for sorry, rho is equal to AT. Sigma will be equal to 1 upon T, right? Sigma should be equal to 1. It should be proportional to 1 upon T, because sigma is proportional to 1 upon T from, and this ratio is a constant. We should be I mean, it should be very clear that thermal conductivity of metals should be more or less constant, isn't it? because sigma is already 1 upon T. So this temperature and this temperature will get cancelled. And if this ratio has to be a constant, then thermal conductivity should be constant for the metals. Am I not audible? Somebody has written that I am not audible. Is it a problem for everyone? Am I audible? Okay. Yes, I think for most of the people I am audible. Aditya, you can maybe check. You can probably check your network connection. Okay. So thermal conductivity of metals should be a constant. I will correct this mistake here. It should be actually 1 upon 2. And this is what we are showing in this plot also, that when we plot thermal conductivity versus electrical conductivity, it is a constant. Like we are plotting this, basically this relation k upon sigma t is equal to c wfl. According to this, there should the plot between thermal conductivity and electrical conductivity should be a straight line, right, passing through the origin. And when we do that with the cwfl is equal to the value which we calculated earlier, you can see that most of the pure metals, they are following the Wiedemann-Franz law. This law is known as Wiedemann-Franz Lorentz law. It is followed very well by the pure metals as well as most of the metallic alloys also. You can see that there are some alloys also in this plot. Like for example, steel is an alloy, lead 40 Ag, brass, all the alloys as well as pure metals. They follow this Wiedemann-Franz Lorentz law very well. Thermal conductivity and electrical conductivity, they are both related to each other by this law which we saw earlier. Now we were discussing the temperature dependence, right? Above 100 Kelvin. So this is a plot of thermal conductivity versus temperature for two pure metals, copper and aluminium, and two alloys, brass and aluminium, 14% Kg. Let us see what is happening in this plot, right? Above 100 Kelvin, qualitatively we can say that thermal conductivity is a constant value. It is not changing with the temperature. We are getting more or less a straight line, right? Why does it have, why that is happening? We know already that the temperature is the thermal conductivity should be temperature independent because sigma is already dependent on inversely proportional to the temperature. So above 100 Kelvin, this relationship is followed very well. Okay, but below 100 Kelvin, we saw in case of electrical conductivity also that electrical conductivity does not follow this simple rule of sigma sigma is proportional to 1 upon T. It is valid only after approximately 100 Kelvin temperature. Below that, there is a stronger dependence on the temperature, right? We saw that it was for resistivity, it was T to the power 5 dependence. So that is why we get different kind of behavior below 100 Kelvin. And the reason for that was, if you remember from last class, that the atoms are actually not vibrating with a constant frequency. The scattering of electrons, that that actually becomes dependent on the frequency of the atoms below this particular temperature, and that is why we get a stronger dependence on temperature below 100 Kelvin. So above 100 Kelvin, this law is followed very well, where we follow the temperature dependence of conductivity, but before that the law is not followed because of the same reason, right? For alloys, we see that, like we saw earlier also, right? For alloys, first of all, resistivity or electrical conductivity, it is very weakly dependent on temperature because their conductivity is dominated by impurity scattering, and impurity scattering is not temperature dependent. It depends only on the concentration of the electrons, sorry, concentration of the impurities, right? So that is why their electrical conductivity is anyway a constant. So there is a smaller dependence on the thermal conductivity that actually is increasing with the temperature, right? Because their electrical conductivity is not directly proportional to the temperature. So that is why there is a weaker dependence, but there is, although I mean it is also qualitatively constant only, but there is a weaker dependence on temperature. because their electrical conductivity is dominated by impurity scattering. It is not dominated by the atomic vibration scattering. We can see here that rate of heat transfer depends on the mean speed of the electron, which is very weakly on dependent on temperature. Yeah, one reason which I wanted to explain is, uh, one physical reason which we can through which we can explain this temperature independence of electron thermal conductivity. As we saw earlier, the speed of electrons is temperature independent, right? And in this case, the heat conduction actually depends on the electron velocity, because only how fast electrons are traveling, only that will determine how fast is the heat is getting transferred from hot region to the cold region. In this picture, if you see here, how fast the heat is getting transferred from this region to this region, only it depends only on the velocity of electrons, right? And this velocity of electron, it is only very weakly dependent on temperature. The gain in velocity comes from the collisions with these atoms, but not from the temperature. So that is why, anyway, from physically also we can see that why their electrical conductivity is not depending strongly on the thermal conductivity is not depending strongly on the temperature, because rate of heat transfer depends on the mean speed of electron, which is very weakly on dependent on temperature. All right. Is it clear, or I was too fast, or there are too many things which have been mixed up? If somebody is confused, you can unmute yourself, or you can write in the chat box if there is any question in this plot. Some important points I will just repeat actually. We get constant thermal conductivity above 100 Kelvin because electrical conductivity follows 1 by T temperature dependence only above this temperature. All right. Below this temperature, the thermal dependency is much stronger. That's why we get a different dependence of thermal conductivity also. We will not discuss this part here, because this will we will discuss in the next chapters. Because if we want to explain electrical conductivity below 100 Kelvin, we need to bring in some quantum concepts, which we will discuss in the next chapter. Okay. Above this temperature, it is clear. The alloys, their electrical conductivity is anyway very weakly dependent on temperature, right? Because impurity scattering depends in the alloys, impurity scattering is dominant, and that depends only on the concentration of the impurities, right? So that is why we see a weak temperature dependence, but not really a very strong temperature dependence. Last point, actually, this is the most important thing, or actually for your visualization also, it should be clear to you that rate of heat transfer depends on the mean speed of electron, which we can see from here. How fast the heat will travel from this side to this side, that will depend only on the velocity of electrons, right? That should be clear. And electron velocity is not determined by the temperature, isn't it? It is very weakly depending on the temperature. It depends only on their collisions with these atoms. The gain in velocity which they get, that comes only because of the collisions from different atoms. And that is why thermal conductivity anyway should be very weakly dependent on temperature, because electron velocity is also weakly dependent on temperature. There are a couple of questions, I think. Let me just see. It is with reference of glass to whole graph. You can unmute yourself. Actually, Saksham, I did not get. Other question is, if temperature is not the reason for increase of velocity of electron, then what is the reason that their vibrations and collisions are increasing in first place? Vibrations of It is not the vibrations of electrons which is increasing. Vibrations of atoms is increasing, and atomic vibrations are dependent on temperature. So, I mean, we are dealing with two different entities. One is electron and one is atom. Okay. Atoms, the energy of atoms, atomic vibrations or atoms, that is dependent on temperature, but the energy of electron, that does not depend on temperature. That's why their velocity is also very weakly dependent on temperature. Okay. And the gain in the electron velocity comes from their collision with the atomic vibrations, which have increased under the influence of temperature, right? Atomic vibrations increase because of that, and when electrons collide with these more energetic atoms, they gain some velocity, and that's why their velocity also increases. Okay, all right, let us move ahead. So what happens in non-metals? uh, Very briefly we will try to understand what happens in metals. Actually, the electrons are heat carriers. In non-metals, as we know, there are not enough electrons. We don't have enough free electrons, so they cannot be heat carriers also, right? So in case of non-metals, what happens is that when they are in equilibrium position, like when the temperature is constant across the whole material, the atoms are basically, we can visualize them as connected through springs, right? These springs are in equilibrium. The atoms are vibrating and whole system is in equilibrium. What happens when we increase the temperature of one end? So we keep this end at cold temperature. Basically, we generate a temperature gradient. Only when there is a temperature gradient, there will be heat transfer, right? So when we generate this temperature gradient by heating this end of the material, what will happen? This atom, the atoms which are in the hotter region, their vibrations will increase, right? They will start vibrating with higher amplitude, and these vibrations will because of these vibrations there will be contraction as well as elongation of these springs. Actually, these springs are bonds. If you want to, you look at it in that way, these springs are actually bonds. These are covalent bonds, let us say, right? So these bonds will elongate as well as contract. For example, here you can say there is a contraction of bond which is happening here, and there is a elongation of bond which is happening here. So this is some sort of wave which is generated, right? And this wave actually gets transferred in case of non-metals, and this is how the heat energy is transferred in a non-metal. The electrons are not charge carriers, sorry, heat carriers. In this case, these vibrations, these are also called lattice vibrations. Lattice vibrations. These lattice vibrations are the medium for heat transfer in non-metals, right? And because these lattice vibrations are the medium of heat transfer, the efficiency of heat transfer depends on efficiency of coupling between the atoms, or basically the interatomic bonding, right? The stronger these bonds, the the stronger or the more efficient will be heat transfer also, right? You can imagine that when you have stronger springs, and if you try to vibrate one part of a there are multiple springs which are connected through atom, through different spheres, and if you try to vibrate one end of the, let us say, this series of springs. The stronger the springs, the faster will be the wave which will transfer through this series of springs, right? So basically, the stronger of the strength or the efficiency of heat transfer, it depends on the interatomic bonding. The stronger the interatomic bonding, the faster will be the rate of heat transfer. Mode of propagation of wave, whether the wave is moving travel to the direction of heat transfer, or it can be also moving perpendicular to the direction of the heat transfer. So that will depend also on the mode of propagation. Then there can be different type of defects. Let us say if you have a grain boundary is a sort of disorder, right? So if there is a disorder, this wave will get scattered, right? It will, some part of it will reflect, some part of it will be refracted, like it will be transmitted. So if you have more defects, the heat transfer will be slower, right? So these are some of the factors which determine heat transfer in non-metals. You can see here, actually there are we have mentioned you can see that we have mentioned the heat thermal conductivity of some of the pure metals. It ranges from 50 to approximately 420 watt per meter Kelvin. In non-metals, some of the non-metals have very low electrical conductivity, like these are metallic alloys. In metallic alloys also, you can see that we can, whatever he has mentioned is about 150, we can get up to 150 watt per meter Kelvin. Just a second, there are some questions, I will address them. Let me just finish this slide. But sometimes we can get in non-metals very high thermal conductivity. For example, diamond. Diamond has very strong covalent bond. Actually, diamond is, as you all know, diamond is one of the hardest material, right? The hardness of material comes from the strength of its bonds. The bonds are so strong. The covalent bonds which are there in diamond, they are so strong that these lattice waves which are traveling for the heat propagation, they are they travel with very high efficiency. That's why they get very high one of the, actually this is one of the highest thermal conductivity material. Diamond is one of the highest thermal conductivity material, although it is a non-metal. The heat transfer happens in the diamond through lattice vibrations, but because of the strength of the bonds, we get very high thermal conductivity in diamond. Okay, so let me just address some of these questions first. uh, First is indirectly velocity is depending on temperature, means if you increase temperature then amplitude of atom increases, then collision amplitude of electron also increases. Yes, indirectly it is dependent on the temperature, but all the energy which is gained by atom when we increase the temperature, that does not get transferred to the electron. In fact, you will see in the next chapter, the gain in energy is very small in the electron when they collide with these atoms. The gain in energy is very small. Actually, it is the gain in momentum. The change in momentum is much more significant. Okay, so you are partially correct that this increase in uh, velocity of electron is indirectly dependent on temperature, but we cannot draw a direct relationship between temperature and velocity of electrons. Can you copy paste this question? Oh, wait. I think I am. There is a lot of confusion. Let me copy paste the question. The question which I was answering now was this one. Somebody was asking that temperature is not the reason for increase of velocity of electron. Then what is the reason that their vibrations and collisions are increasing in first place? Then actually, yeah, there was a follow up of this question. The follow up of this question was this: indirectly velocity is depending on temperature, means if you increase temperature then amplitude of atom increases and collision amplitude of electron also increases. So I just explained that indirectly it is sort of depending on temperature, but even after that it is not directly dependent on temperature, because all the energy which is getting transferred from atomic vibrations to electrons, that is not really depending on temperature. Reason for higher thermal conductivity for diamond. Okay, see, diamond higher thermal conductivity we saw in this previous slide, that when the heat is getting transferred through lattice vibrations, it depends on the strength of interatomic bonds, right? The stronger these springs, or you can basically, we are trying to visualize bonds through springs. The higher the spring coefficient of these springs, the faster will be the wave which will be traveling, right? So we can say that the stronger the interatomic bonding, the faster will be the transfer heat transfer which will be happening in the material. So, and in diamond is one of the hardest material, and its hardness actually comes from the strength of its interatomic bonding. There are actually very strong covalent bonds in diamond, and that is why, because of these very strong bonds in diamond, we get higher thermal conductivity in diamond. So the higher thermal conductivity of diamond is coming from its very strong interatomic bonding. Is that clear now, Anchit? Okay, let me see. Somebody below 100k, k is proportional to t square. It looks like that, right? When we look at this curve, it looks like that it should be proportional to t square. But the relationship is not exactly t square. We will actually we will not deal much with thermal conductivity in this course, but if you want to read in more detail, then you will see, actually, because of this, you will, the actually we need to read a lot of lattice dynamics if you want to understand the thermal conductivity of non-metals. Then it is understood through uh, discipline called lattice dynamics. And these lattice dynamics, they are not really harmonic. So that's why we cannot really say that these are, although it looks like parabola somewhat, but that dependence is not exactly T square. I can answer only that much as of now, because we are not like, we don't have enough prerequisite knowledge for discussing this part of thermal conductivity, which is below 100 Kelvin. Okay. Yes. Any question which I have left, I did not answer. How mode of propagation of wave is a factor for heat transfer? Okay, so one question is propagation of how the mode of propagation of wave is a factor for heat transfer. Let us look at this thing here. Where is the plot? Okay, so as I explained, right, mode of propagation, or basically it can be either the wave can either be traveling parallel to the direction of heat transfer, or it can also be traveling to the it can also be traveling perpendicular to the heat transfer, right? So when it will be traveling, there will be the contribution will be completely in the heat transfer. But when the wave is traveling perpendicular, like there are vibrations perpendicular to the direction of heat transfer, then some amount of energy will be lost, in the perpendicular direction, right? Because ultimately we are concerned about heat transfer in this direction, right? So some amount of energy will be lost in the perpendicular direction. That is why the mode of propagation also becomes an important factor in the when we are discussing about thermal conductivity. Okay. Any question which I have not answered, you can type again in the chat box. Okay, I think we have exhausted our time today, so we will stop here. Maybe in the beginning of next class, we will take up. If you have any questions, we will take up those questions. Otherwise, we will start with the next topic. Okay, thank you everyone. We will meet on Thursday for the class.